Thank you so much, Ben. And thanks to the classes for inviting me. So today I'm mostly going to talk about Serre functors and a little bit about recollements and even less about approximability. So this is a project I've been working on with Bregje Pauwels, and a part of the inspiration of the project is categories, they call them categorifications. However, the part that's done is mostly the formal part, so there will not be much categorification in this talk. But it's definitely part of the inspiration. All right. So I don't know if you can read this. It will mostly be darker than this, but it's just a phase of field. And I'm hoping, and I think actually that all of this works for an Artin ring as well, but I'm sure that this type of audience doesn't mind letting K be a field. So let's do that. All right, so we're going to start with an example. Let X be a smooth projective variety of dimension n. And then let's consider canonical sheaf. Then probably at some point in your career, you've seen Serre duality, which is this statement. It says if you look at two objects in a derived category, or you could just let f and g be G's, then their Hopf spaces, in other words, their extensions, will satisfy this property. So you can switch f and g around so that you get a k dual on the left-hand side, and on the right-hand side, we're going to tensor with canonical sheaf and shift by the dimension. So this is classical Serre duality. Very useful. I'm sure I don't have to convince you of that. But the same can be done in other categories. So we could let A be some finite dimensional K algebra and look at its dual. Then we can consider this functor, which is just considering the dual of A on the derived category. And if we inside derived category look at the homotopy category of projectives, bounded homotopy category, and then apply that function to it, we end up in the homotopy category of injective modules, bounded homotopy category. Okay. So Nakayama sends the projectives to the injectives. And again, we have this nifty formula, this natural isomorphism in derived category for any bounded complex of projectives X. It goes to the other side, but we have to apply the Nakayama functor to it. Right. Okay. So as I said, these Serre functors are very useful. For instance, for varieties, they've been used to show that you can actually build up a variety from the derived category of coherent sheaves of the varieties smooth projective. And there are many more applications. So we want to know, when does a algebra have a Serre functor? I haven't yet defined what a Serre functor is, but when is there some functor that has this property? So if A is a Gorenstein algebra, so still finite dimensional, then actually the bounded homotopy category of injectives is equivalent to the bounded homotopy category of projectives. And so we actually get an autoequivalence of the bounded homotopy category of projectives. And this functor, this autoequivalence, will satisfy that formula. If moreover, we have that A actually has finite global dimension, then both of these are equivalent to the finite derived category of finite generated modules over A. And so we actually get an autoequivalence of the derived module category. And again, it's not to be satisfied. So here, a functor that has this property, we'll call a Serre. Right? Okay, so maybe it's a good time to make several points. I think many people know about Serre functors, know about Serre duality, but think of it as a phenomenon that only occurs in finite global dimension. They say Serre functor is finite global dimension. And one point that I want to make in this talk is I don't think that is the right way to think about it. Yes, if it had a finite global dimension, you can get the Serre functor on the bounded derived category. But that's, in fact, we should always be looking at this category. This is always where Serre functors occur. And if A has finite global dimension, it just so happens that those are equivalent. But more generally, for any Gorenstein ring, we still get this autoequivalence on the bounded homotopy category of projectives. And what if A is a general ring? We could still look at the injectives, the bounded derived category. Where is it? We could still just look at this category, and maybe it will be an equivalence of one category, but it will still be an interesting functor with an interesting property, right? Okay, so let's define Serre functors. So we start off with a triangulated category. We're going to assume for now that all the common spaces are finite dimensional over the field. And then some autoequivalence of the category is a Serre functor. If for all x and y, we have this natural isomorphism that holds naturally in x and y. A very cool fact about Serre functors is that if they exist, then they automatically will respect triangulated structure. So it will automatically be an exact functor. And less surprising is that it is unique up to the canonical isomorphism. If you fix the stories of this natural isomorphism, if you make that part of the data. Okay, so what do we have so far? If A is Gorenstein, we get a Serre functor on the homotopy category of projectives, finitely generated projectives, I should say. If A has finite global dimension, we get a Serre functor on the bounded derived category of finitely generated A modules. And for any finite dimensional A, we still get a functor. We don't call it a Serre functor because it's not an endo functor. It goes from the projectives to the injectives, but it still behaves like a Serre functor. And so why not consider it? We get these two subcategories that are equivalent, and they are sort of Serre dual to each other. All right. So the bad news, very few rings are Gorenstein. And so few homotopy categories have Serre functors. Now suppose that we know some category has a Serre functor, it could still be very hard to compute. For instance, you have established that some category is of the form derived category of A modules for some algebra of finite global dimension. So you know it has a Serre functor, but A is just some endomorphism algebra of some exceptional object in your category or something. You don't have an explicit description of it. And so you don't explicitly know what A is. That would be an example where it will be very hard to compute the Serre functor. Okay. We also have some good news. The good news is that, as we've seen, instead of thinking about Serre functors, we can think about partial Serre functors, which always exists, always meaning in all cases that I care about, and even more so in all cases that you people care about. And second good news is that if you're working with commutative rings, commutative, or even generally with schemes, you can test Serre duality locally. So for instance, you could cover with open affines, and then if you've covered by Gorenstein rings, then your original ring was Gorenstein. So you can test locally, and the main goal of this talk is to try to take that idea of testing things locally and use it for triangulated categories in general. Okay, so now starts the formal bit of the talk, which hopefully will not be too painful. I promise that after we've gone through the formal bit, there will be some explicit categories and some explicit examples and some explicit computations. But formal theory is important too. Right, okay. So we're going to take some triangulated category. We're going to assume it has all co-products. So now it's a big category that no longer has 5-dimensional Hom spaces. We're going to assume that it has some compact generator, G. What does that mean? G being compact means that Hom spaces out of G as a functor commutes with co-products. And it being a generator means that for any non-zero object, there is at least one morphism from some suspension of G into it. Okay, so you can test being non-zero on maps from G or in its suspensions. Okay, so our first example is going to be a derived category of a ring, any ring. And this is going to be, I was trying to make it a little bit less unappealing for non-category theorists. So I'm going to have to as a running example for the talk. But then Ben said that some of you don't like derived categories, so I don't know, but if that, yeah, I have bad news for you if that's the case, because yeah, so this is going to be a running example, and we can just put G in degree 0, and it generates the whole category.
I did only say some.
Some, yeah, a couple. Okay. So we could also let T be the homotopy category of spectra. So that's a typical example from algebraic topology that I care about. You could take X and quasi-compact quasi-separated scheme, and then there's a theorem by Bregje that there is a compact generator. It's just an existence proof. It's no construction, but there is some compact generator. Or you could take some DG algebra and take derived category. These are all examples where you have some compact generator. Okay, now we're gonna talk about approximability, which I'm gonna use as a black box. So I'm not gonna give any precise definitions. However, this is such an amazing idea and a great tool. So I just wanna give you a vague idea of how it works. And I wanna encourage all of you to read about it or ask me about it. So, first of all, we're going to say, okay, we want to approximate things in a category by easier objects. And what does easy mean? An object should be easy if I can build it in finite many steps out of my generator. That's easy, right? Secondly, if I'm going to approximate, I better have a metric. So we're going to have some metric on our category. You could consider many metrics, but in fact, there's going to be a canonical metric. I won't define it, but I can say that the balls around 0, so the objects that are close to 0, are, I don't know if you can read this, but they're essentially built out of many negative suspensions of my generator. Okay, so I'll do the example of the derived category of a ring in a bit, so maybe that'll help. But so the fewer positive suspensions of the generator that you use, the smaller the object gets, or the closer to 0. Okay, so if you start off with a ring, then the balls will just be around 0. They will get smaller and smaller as n gets bigger and bigger. So the further and further your complex is to the left, the smaller and smaller your tail gets, that's closer to 0. Okay, and now we call a category approximable if all objects in here, so here I'm assuming that there is some T structure, which is also canonical, but basically all objects that are in some way bounded above can be approximated by easy objects and I want to be able to approximate in some uniform way. So that means if I want to approximate by a ball of 1/5 or whatever, then I can choose my n and my I and my j in the same way for all objects. Okay, so I want to do it in a uniform way. All right, so let's do an example. All right, so we have an algebra. We take a module over that algebra. I'm sure all of you have done this before. Very often, if we want to solve some problem, we're going to do it by taking a projective resolution. And then in the derived category, the object M will be isomorphic to a complex of projectives. Okay, so now we can take that complex and we can truncate. Let's say we're going to truncate here. So truncating means that I'm putting it in a triangle. So in my first step of the triangle, I'm only going up to minus L plus 1. And the middle one is just my original object. And at the end, I have this leftover bit that can keep going, right? And you can really see that you can let L be however big you want. And the bigger your L gets, the smaller and smaller your tail gets, the more and more left to go. So you're in a ball closer and closer to 0. Right? So we are approximating by these objects. And these objects can always be built out of my generator A infinitely many steps. Right? So this is the proof that the derived category of A modules is approximable. Okay, any questions so far? Yeah.
I guess the question I was, the subscript n means
Yeah,
these
an extension. So what we're going to do is we're going to start with suspensions of G between minus I and J. The bar means we're going to allow all coproducts, so all possible coproducts. And then we're going to take extensions n times, and then we're going to take summon. Yeah. More questions? So yeah, the purple bit is for people that have seen this notation before. I didn't feel like really explaining it.
Sorry, can you say what uniform way?
So that means that that if I choose say this here, I am approximating up to minus L here, then I can choose my n and my I and my j on a way that only depend on L and it do not depend on the object. Yeah.
So it doesn't have to be linear or anything, can be as long as the function depending on L.
Yes, that's right. Yeah. But there is so this is all due to Neeman, and he's written down an actual so for the ring A, it's not hard to write down. Okay. Yeah, so as I said, this is all due to Neeman. It's amazing stuff. It's the kind of stuff where you're like, on the one hand, like it's such an obvious thing to do. Like mathematicians, we approximate all the time. Why hasn't anyone thought of that before? And on the other hand, you're like, it's so intricate. How did he ever think of that? So it's like kind of that mixture of both. But yeah, he has a great ICM paper that I highly recommend you read. And I'm happy to talk about it if you're interested. So approximability is a black box. I'm only going to mention it once again at the end when I state my theorem, but you will not need it in the rest of the talk. So if you got lost there, don't worry about it. Okay, some examples. Again, derived category of a ring, just proved that. Homotopy category of spectra. If X is quasi-compact and separated, derived category will be approximable. This is not easy to prove, and it was proved by Neeman. If you start off with a Bregje algebra that has no positive cohomology, then you're also in an approximable category. Okay, so many examples. I think all examples that most people here would care about are approximable. Okay. Then it's a theorem by Jesse Berg, Neeman, and me that if you take two such approximable categories, you can glue them together along a recollement, and then almost always the gluing will again be approximable. So you can glue these together and you build a new approximable category. So that's not what this talk is about, but we will need it later.
Bregje,
Yeah.
could you give like example of one of those three, which is a bit harder? Like I don't think I understood the difficulty of the approximability from the example.
So this one would be hard. So these two are easy. This one is easy, this one's hard. For one, there's no explicit description of the generator. So I don't know what easy proof you have in mind.
Well, I guess it was like in D of A, it was the complexity. Well, like it seemed like it was very easy because it was possible. And it's, yeah.
Yeah, it's not. Yeah. Okay. So partial Serre functors, we already talked about that. So I defined what a compact object was. Those were the ones where morphisms out of it as a functor commutes with coproducts. So we write TC for that. So for instance, if T is the derived category, then TC will just be the bounded homotopy category of projective A modules. So very familiar. We think of these as a small objects, so they're small enough. And they behave well. And we can look at this functor for any such compact object X. And now this functor will commute with coproducts, and it's a cohomological functor. So by Brown representability, it's in fact representable.
What's the check on the TX line?
Is K-dual. Yeah, so even though y is on the right-hand side, this is a contravariant functor because of the Okay, so it is Brown representable. So starting off with a compact object, we get some other object in T that represents that functor. So in particular, we get a natural isomorphism given here. Okay. And now, because of this natural isomorphism, in fact, this is going to be an equivalence onto some subcategory of T. And so one point of this talk is that instead of always looking at Serre functors from TC to TC, we should be looking at the functors from TC to whatever the image is. And it will, I'm guessing that it will still be a very interesting functor and might have applications. Okay, so such a functor is called a partial Serre functor. And if it actually does end up in TC, then it is called a Serre functor. Okay. All right. Okay, last formal bit is recollements. So instead of giving you the definition of recollement, I decided to draw a bunch of recollements and hope that at least one of them is familiar to you. So given a topological space, you could look at an open subset and its complement. And then I think almost all of you will have done this. At some point, you get these 6 functors that fit together into a recollement. So a very famous application of that is when you start off with some stratification of X, then you get this recollement of derived categories of sheaves, whatever sheaves means in your particular context. And yeah, that's how one way to build perverse sheaves, for instance, right? You glue them together, you change the T structure, and the heart gives you the perverse sheaves. All right. So you might have seen this before. If you start out with a scheme and you take some open quasi-compact subset and its complement, then again you have a recollement, but this time we're going in the opposite direction, which is kind of weird and unexpected. So here we get a recollement going the other way. If you have a highest weight category, I included this example because I know you like highest weight categories, most of you. So whenever you have highest weight category, you get some filtration of that category. And each piece fits into a recollement like this, right? So this is a great way to do things by induction. Here, this is just a division ring, so a very easy category to understand. Here, you've gone down from I to I-1, and so very often if you want to prove something about AI or about A, you're gonna use what you know here and what you know here and then put it together. Okay. And another example, if you have two algebras or even each algebras, you can build the lower triangular matrices ring. You get a recollement here. So this example should also be quite familiar to you. And then this is how I think about recollements. If you start with a triangulated category and you take some set of compact objects, you can build the subcategory of T that is generated by those compact objects. You can embed it into T, and then you get a bunch of adjoints which give you this diagram. Okay. And so actually at least the first three, or I think actually all four are examples of that. Okay. What should I say about recollement? So in all of these cases, you definitely get the sense that you're taking two categories and you're gluing them together. So how do we make that precise? So we have 3 rows. Each time the lower row is right adjoint to the row above it. All of these are a subcategory and a quotient. And each object here can be put into a triangle of an object coming from here and an object coming from here. So in that sense, it's really this category here is glued from objects here and objects here, right? So you should really think of recollement as gluing two triangulated categories together. And then another remark I want to say is, in many of these examples, you really do only get the recollement on the derived category of all A modules. So not finitely generated modules, not the homotopy category of projectives. Really, we want the derived category of all A modules. And that's going to be a bit of an issue because Serre functors are always defined on the compacts, right? So yeah, we'll get back to that. Okay, so we're gonna have 3 triangulated categories. We're gonna have compact generators, and we're gonna assume that the Hom spaces of the extension of those generators are all finite dimensional, because we want to be able to take duals, and we don't want Hom spaces in very high degree, or we don't want very high extensions, and we also don't want very low extensions. So they should be almost zero, almost everywhere. Okay, so we're going to have some recollement. So A is glued together from B and C. And I told you that partial Serre functors always exists. So let's build partial Serre functors on A, B, and C. And the reason I have this dotted line is because, as I said, these are usually the big categories, unbounded derived category of all A modules, for instance, whereas these will be defined only on the compact objects, for instance, the homotopy category projective. Right, so this is not an actual functor, it's only defined on certain subcategories here. And now we would like to know, given a Serre functor here, given a Serre functor here, then you would. So this question has been asked before, and it has been given answers before, but as far as I know, all the answers come from the recollement where is it actually a recollement where the Serre functor exists. So on the homotopy category projectives, which is a pretty rare case. Okay, how am I doing for time? Okay, that's perfect, I think. Okay, so let's go back. Any questions? Yeah.
Did you understand the question right? That if S, C, and SB are not just partial Serre functors, but actual Serre functors, can you include SA against? That's the question.
Yeah, that's an example of a question. Or can you describe SA in terms of?
What?
But this is an example.
I would like to,
That's the question I'm supposed to have in mind.
that's a question I would like to answer, and the second one is, can you describe SA if you know S B and SC? Because an actual construction is also important. Yeah. Yeah, okay, so the top row always preserves compact objects. That's just formal nonsense. So suppose that we have set of functors. We could go from one compact object to another compact object and then go down. Or we could go down and then we could go up or down like that, right? And so it turns out that the way this diagram commutes is it actually switches around the two adjoints. So here I would down a proof, but you can ignore that if you like. So it's just by, again, by formal, a very easy argument, this definition of adjoints and the definition of Serre functors. Again, I'll show you in the picture. If you take the upper adjoint and then you do the Serre functor, do the same thing as doing the Serre functor and then take the lower adjoint. And the same thing on this side, top Serre, Serre, bottom, right? So we're going to switch the two adjoints around, same on the other side. And here, I've tried to color it in the picture. I don't know if you can see that. All right. So this is always true, no matter whether these are partial Serre functors or actual Serre functors. But now let's suppose that they are actual Serre functors. So in particular, if I apply the Serre functor to AC, I end up in AC. So the Serre functor applies to the compact object. So also if I apply the upper star to it, this should still be the same category. So just a dumb statement. Another consequence is that in fact, not only this one preserves compacts, but also this one preserves compacts. Because how do I prove that? Starting, okay, the compact here actually comes from compact here and then a Serre functor. And so, and the compact here comes from Serre functor here, like that. So actually going around gives me a Serre functor. So here, if I start off with a compact here, I go to a compact. So again, just a formal consequence is that not only does the top row preserve compacts, but also the bottom row does. The middle one in general will very rarely preserve compacts. Okay, so we wrote down these three immediate consequences that happen when we do have actual Serre functors. And so you can ask, is that enough? So we're gonna look at a recollement. This is where we need approximability. It's using a proof. So you can just ignore that if you want. So we have three approximable categories, some recollement that satisfies these three conditions that we certainly need. And then there's a third condition that uses some notation that I didn't feel like explaining, but it is very mild. So again, you can choose to ignore it if you like. So that's, those of you that know what this means. So this is an extra condition. Okay, so the following are equivalent. We get the Serre functor on the compacts of B and C, so on left and right. If and only if we get a Serre functor on the compacts of the. Okay, so even though we didn't have an actual recollement on the compacts, we still got enough information from the recollement to conclude existence of the Serre functor. Okay. So that's good. That's sort of taking that good news that we had before, where we could test whether a ring was Lorentzian locally, and making it more general. Okay, so this is a generalization of that. The other good news that we had, or no, actually the other bad news that we had was that it was hard to construct functors, Serre functors. And so it would be good if we could actually construct a Serre functor on A from a Serre functor on B and a Serre functor on C. I do not know how to do that, but I do know that if you start off with a good guess, so if you start off with some functor F, it is some other equivalence of the compacts. Then you can use the element to test whether it is a Serre functor. So you have to start off with a guess. And the way you do that is you just check that it satisfies what we certainly needed, namely that the Serre functors switch the adjoints around, switch the top and the bottom adjoints. So as soon as you have that, then you know that if the two outside ones are Serre functors, then f is going to be a Serre functor if and only if it switches like doing this, and then the bottom adjoint is the same as the top adjoint. So it's not actually constructing a Serre functor, but it is testing whether a given functor is a Serre functor. I think we are, yes, okay. So this is the last triangulated category bit, and all the rest is going to be very concrete. So any questions? Yeah.
So that thing has the gene has the
Sorry?
you have the gene has the
Yeah, I mean, you can always construct that, or what do you
I suppose you have S, B, and C, all the categories are. Can you construct the Serre functor out of it?
I see. I don't know.
Because it looks like just some color.
Yeah. I don't know. Maybe, yeah, if you have an idea, I'd love to hear it. So. Okay, so we're gonna focus on the example with the 5-dimensional algebras. So let's take two 5-dimensional algebras and glue them together in a lower triangular matrix. And then, as I said, we get this recollement. Okay. So you can do that, glue them together and get a more complicated algebra, and you can do that several times until you have the algebra that you like. If you have a nice enough algebra. Okay. Now, if you actually write down these functors, I that's this one, is going to send the ring to the B module Bn. And J lower star is going to send the ring C to this module over this ring. And G star is going to send the Serre functor of this, so the dual of this, to this row matrix module over C. Okay, so I've just written down explicitly what they do, at least on the generators. And we want to test whether this is a good recollement, whether this can tell us if I know that C and B are Gorstein, whether this one is Gorstein. So what do we need? We need that the lower ones preserve complex. So if I start off with a projected module here, I should get a bounded complex of finitely generated projectives. When is this going to be a bounded complex of finitely generated projectives? Well, n will have to be projective over B, or it will have to be at least have finite projective dimension. Doesn't have to be projective. They should be perfect over B. Should have finite projective dimension. Okay. Same here. This one has to preserve compacts. So this one here should be perfect over this, and you can check that happens when M is perfect over C. In other words, when M has finite projective dimension over C. So what do we get? We need that M has finite projective dimension over B, and M has finite projective dimension over C. And in that case, we are in a good recollement, so that you can actually glue Gornsteinness together across the recollement. So the lower triangular matrix algebra is going to be Gornstein if and only if M is pi perfect. That just means that it has finite projective dimension both over B and over C. And I'm sure this was this was known before. I don't think this is new. But if you have a reference, I'd love to know. And a fun fact in this particular case, that's actually pretty rare, is that in that case, you actually get a letter that just continues forever. And it's given like just by conjugating with the Serre functors in each step. Okay. So let's do a more specific example where we let all our rings just decay. And so we're gluing two copies of decay together to make a new algebra. And certainly K has finite predictive dimension as a K module. And so it already satisfies the conditions. So we know that there is a Serre functor here. On the compact at least. We know that this is Gorenstein. Now what is a Serre functor here? Does anyone know? That's the identity functor, and here as well. So does that mean that if I take two times the identity and I glue them together, should I get the identity? No. Good, yeah. So we know that it's Gorenstein, but the Serre functor will not be the identity. In fact, this is not even a Calabi algebra, so that means the Serre functor is not even just a suspension. It is a little bit more complicated. So your resulting Serre functor is going to very much depend on how you glue those two copies together. Okay, so it's an indication that this constructing the Serre functor is not that easy or that obvious, at least from the recollement. Okay. Last example. We're going to take this quiver Q, and then take path algebra and mod out the relations theta squared alpha beta. And then I have this projected P1 from the X1. I can look at the subcategory generated by a P1. It's compact, so I get this recollement. And I can write down a more explicit description of each of those pieces. So this one is generated by projective. You can think of it as derived category of the endomorphism ring of P1, and you can easily compute that. So it turns out that this is just decay again. So definitely Gorenstein. Here. So these are the ones that are orthogonal to this subcategory. A little more work you can compute it, and you get that this is actually the derived category of kx over x squared. So here we get again a Gorenstein ring, not finding the whole image. So this is an example where you don't have Serre functor on the boundary category, but you do have one on the topic category for this. Okay, so we've glued two Gorenstein rings together. Will the middle one still be Gorenstein? So for that to happen, it is necessary and sufficient that this recollement is good. And so we have to check that the bottom ones preserve compacts and the middle one does what you want it to do. So how did I check that? So I've computed J lower star on this one, and we need it to be sent to a projective. But it's being sent to S1, which is the simple module. So it is not being sent to projective. So in particular, this is not a good recollement. And from there, we can conclude this one is not Gorenstein.
It's not perfect. You need it. Perfect would be enough, right?
Yeah, sorry, perfect. I think that's it. Yeah, I'll stop here.